Korea Science Academies of KVIS, South Korea. Please begin the presentation.
Hello, so I'm Josh and this is KVIS, and we're here to talk about our research regarding the conversion of waste cooking oil to biodiesel using the process of transesterification. So the aim of our research was to find the catalyst that could do this process both efficiently and cheaply. But first we'll start with the motivation behind our research. So globally, over 34 million liters of waste cooking oil are produced each year, and this comes from all countries around the world. But the issue is that in underdeveloped countries, there is no proper disposal or treatment process for this waste, and that's the basic reason of our research. So now we'll look at the theoretical aspect.
So basically what waste, an oil is an oil is just glycerol with 3 fatty acids, but a waste cooking oil, what differs it with, compared to oil is that the waste cooking oil, there is contamination with water and high heat due to the cooking process, and thus the triglyceride combined with water forms glycerol and 3 fatty acids. So the thing is that water breaks the ester bonds between the glycerol and 3 fatty acids, and if we try to go directly to the transesterification process, there is a creation of soap. As you can see, one example of free fatty acid that can be found in many waste cooking oils is stearic acid. So the stearic acid, when combined with catalyst that usually sodium hydroxide, it forms soap and glycerol. So again, due to the reverse reaction, the soap combines with water again to form stearic acid and sodium hydroxide, and thus we have to be able to pretreat it before going to the transesterification. So for the pretreatment, we first have to measure the amount of free fatty acid by using titration. So usually a lot of literature, what they do is they do acid-base titration and measure the amount of free fatty acid by using NaOH, and then later on by using sulfuric acid or any other type of high acidic property chemical. They neutralize it, and then later on they do the transesterification. So that is the process that they do.
So now we'll go into our reaction and experimental process. So for the production of the catalyst, we used a Ballman procedure, as you can see here. We also attempted a solvothermal procedure, but our results were not successful with that. And this is our transesterification reaction setup with the condenser, the glass reactor, and the hot plate and silicon foil pad.
So basically what makes our research very special is that there are some quite literary works that has been done for the esterification process of waste cooking oil, which is for zeolite, because zeolite has the property to absorb free fatty acids. But what makes our research special is that we use zeolite with sodium methoxide, and because the methoxy ion gives zeolite active sites by using oxygen. The surface layer, we made the sodium methoxide be embedded in the zeolite so that we can bypass the pretreatment and directly go from waste cooking oil to biodiesel. And another reason why we use zeolite is because of the structural support that it gives. This is after 2 months of our reaction. It's quite stable compared to other type of chemicals in which they go degraded and becomes solidified.
And with our catalyst synthesis, we also wanted to test the incorporation of the sodium methoxide into the zeolite. So our first step was FTIR analysis, and with the peaks here, roughly in the 1,000 to 2,000 range, you can see the incorporation in our catalyst, but a better explanation of this can be seen with our X-ray diffraction analysis.
So for the XRD, basically this is about our hypothesis for the entropy. So if you can see the zeolite compared to the zeolite sodium methoxide, which is our catalyst, you can see that there is a decrease in the crystallinity. That means Later on, we also did SEM and TEM to analyze the surface composition of our catalyst, and you can see that there is a decrease or there is an effect made in the surface structure of our catalyst. Oh, also for the bed surface area, it's quite similar to the XRD. We just compared it to the zeolite and catalyst. This also further emphasizes on how there is an effect made in the surface, which is a decrease in the crystallinity. Also for the SEM, if you compare, this is our zeolite and this is our zeolite sodium methoxide. If you can see the zeolite sodium methoxide, there is it is more disorganized. That further emphasizes our XRD and bed surface area. And also if you can see the TEM, basically SEM and TEM is quite similar, but for the TEM, it showcases the inner or the nanoscale, what the structure looks in nanoscale. But we further we further understood that there is no more difference in the nanoscale level, and only the crystallinity differs in the outer layer or the surface level, because there is no difference made in the inner structure compared to the zeolite and sodium methoxide zeolite catalyst.
So another major phase of our research was the kinetics, because we had to determine the optimum conditions for our transesterification reactions. So we tested 4 variables. This is the methanol volume, and as you can see, around 4 milliliters of methanol was where we found the optimum phase separation between the biodiesel, glycerol, and catalyst layers. And then also at higher levels, we found that the excess methanol was also causing some kind of deactivation process with the catalyst. We also tested temperature, and the pictures aren't here, but we found our optimum results at 55 to 60 degrees Celsius with a 30-minute reaction time and a catalyst loading of 20%. Sodium oxide is really our best biodiesel. So then our final products, which were the waste cooking oil, biodiesel, and glycerol, and the initially used waste cooking oil, we did an FTIR analysis. But this isn't sufficient to determine whether our final product was indeed biodiesel, so we also did a proton NMR analysis. And here, in the waste cooking oil, if you see at 4.1 to 4.3, there are the methyl protons of the glycerol, which are absent in our biodiesel, together with the fatty acid methyl ester P at 3.6 ppm. This suggests that our final transesterification product was actually biodiesel.
Yes. Of biodiesel, but if you go to the NMR of waste cooking oil, then there is no waste fame. That's how we were able to conclude that there is biodiesel in our product.
Right.